So last time we learned subgradients, a topic that's maybe not the most exciting of topics in this course, but it's super fundamental. So you guys will thank me later in the course when you kind of see subgradients popping up everywhere for going over this carefully. So I wanted to go over an example of how we used the subgradient optimality condition we learned last time, and then we're going to jump today into the subgradient method for minimization. So just to remind you of this fact, we learned last time that for any function f, and this is true whether it's convex or not, so this is just really any function, a point x star achieves the minimum of that function if and only if 0 is a subgradient of the function at x star. So this generalizes the zero gradient condition that you would have seen maybe before, previous classes, because when f is convex and differentiable, its only subgradients at any point are its gradient at that point. Okay, so we learned this last time. We proved it. It's just one line right from the definition of the subgradient. Subgradients being an affine underapproximator, a linear underapproximator of the function. And we saw its consequences, and here's one we didn't get to that I wanted to go over. There's a part here on the optimality conditions for the lasso that I'm going to skip because we'll come back to that when we talk about the KKT conditions. Do take a look at it if you're interested. But let's look at a very simple case of the lasso problem, which is a case where the predictor matrix X is just the identity. Okay, so this problem is you're given y, a vector. You want to find the beta, the vector beta, that minimizes the squared error loss to y plus lambda times the L1 norm of beta. Okay, so this is like, for example, doing lasso regression, but without any predictors. It's just having the identity matrix as the predictor matrix. So what is the solution to that optimization problem? It's one that we can write down in closed form, unlike the lasso, say, in general. And you may have seen this fact pop up in other places, but the answer is that the solution to this problem is the soft thresholding operator applied to y. So I take every component of y, and I soft threshold it, and that's by an amount lambda, and that's the solution beta. So let's just define soft thresholding here. Basically, soft thresholding is an operator that goes from Rn, you can think about, to Rn, and that you can just apply it component-wise. It's just the same function applied to each component. And what is that function? In the ith component, it looks at yi, and if yi is bigger than lambda, it subtracts lambda from yi. That's what it gives you back. If yi is smaller than minus lambda, it adds lambda to yi. Otherwise, it sets y equal to 0. Okay, so I think I have a picture on this next page. This is just what it looks like in one variable. So let's suppose this is y, or yi, and this is just the 45-degree line is just showing you what y scales like. So the soft thresholded version of y, it just sets y equal to 0. In this case, lambda was a half. If y lies anywhere between minus a half and a half. Otherwise, it subtracts a half from y if y is positive, or it adds a half to y if y is negative. So it thresholds, which means it sets y to 0 if y takes a small value, where small is defined by less than lambda in absolute value. But it's a soft version of the thresholding operator, which means that it doesn't actually retain the original values of y. It still actually makes them smaller. So one thing that makes this function nice is that it's actually continuous in y. That's maybe one property that makes it a nice function. Okay, so this function completely describes the answer to this problem. The answer to this problem is just take the y's, and in each component, soft threshold it by an amount lambda. That's the corresponding component of the solution. Okay, so we get a sparse approximation to y. It's sparse because if y was ever less than lambda in absolute value, the corresponding component of the solution is 0. Otherwise, it's just shrunken towards 0 by an amount lambda. So let's prove that. We can actually prove that right from the subgradient optimality conditions. And let's actually take one step to get to here. because we didn't actually go over the previous example, so we're not going to see where that came from. The function, right, our function f is just this guy. And what are the subgradients of this function? Well, subgradients of this function look like a gradient of this part plus a subgradient of this part, right? So let's just say subgradients at a point beta are the gradient of this part, which is the gradient of this term. So I know you guys know this. Somebody shout it out, please. So it's not y minus beta, but beta minus y, right? Plus lambda times a subgradient of the L1 norm at beta. We'll just call that S. So where S is, let's say, an element of the subdifferential of the 1 norm of beta, which means that, recall, we have Si equal to the sine of beta I if I is not equal, if beta I is not equal to 0. And otherwise it's anything in between minus 1 and 1 if beta I is equal to 0. So that's the this is the subgradient of the L1 norm, or a subgradient of the L1 norm at beta. Okay, this is true for all I going from 1 through n. Okay, so we want to choose beta so that we can make this subgradient of the criterion equal to 0. Right, so let's set equal to 0. Now set to 0. We get yi minus beta I is equal to lambda times si, right? And I'll just write it out. That's equal to lambda times the sine of beta I if beta I is not equal to 0. Otherwise, we have yi minus beta I is equal to lambda times something in between minus 1 and 1, right? Because that's what si would be. I'm just going to abbreviate that by saying that this is true. Right? Equivalently, I can write that as the norm of the absolute value of y minus beta I is less than or equal to lambda. So these are the subgradient optimality conditions. If we can choose a beta for which this is true, this set of conditions is true, then that beta is the solution. And is the solution unique here in this problem? Is there more than one solution? Pretty sure you guys know this also. Somebody shout out, I'll tell you it is unique. Why is that true? Somebody tell me why it's unique. Just shout it out. Right, the problem is strictly convex. Right, so I have a quadratic term here. The Hessian, for example, of this quadratic term is just the identity. It's clearly positive, strictly positive definite. Okay. So these are the conditions we're trying to fulfill, and if we fulfill these conditions, we get the unique solution. So since I gave you the answer, soft thresholding, you can let's just go ahead and plug it in and see if we can make these conditions satisfied. Okay. Alternatively, I claim you could have stared at these and derived soft thresholding. It's just a matter of what your perspective is. So let's now plug in beta to be the soft thresholded version of y. That's how we would write it. And see if we can satisfy these things. We can just do it component-wise, right? We can check that it's true for each I. And there's really just 3 cases we have to think about. Let's think about the first case, when yi is bigger than lambda. When yi is bigger than lambda, then we're assuming lambda is positive here. Then this is going to give us, we're just going to get yi minus lambda, right? Beta I is just going to be equal to yi minus lambda. And assuming lambda is positive, say, that means that beta I is not 0. So we have to be satisfying this part of the subgradient optimality condition. Yi minus beta I is equal to lambda times the sine of beta I. The sine of beta I is just 1 because beta I is going to be positive. And so we can see that indeed we have, just by rearranging, of course, this being true. And so we've satisfied that condition. When yi is less than minus lambda, I'll just say it's similar. Similar argument gives you the same thing, the same check holding. And when yi is between lambda and minus lambda, then beta I is 0, right, by definition of the soft thresholding operator. And that means we have to see if we can satisfy this condition, right? And that's clearly true that yi has absolute value less than or equal to lambda by construction of this case. So we have that part of the subgradient condition is also satisfied. Okay, so it was easy to check that we have the optimal solution once I told you it was soft thresholding. As just as a test of whether you kind of understand the nature of these conditions, you might also try to stare at them and see if you could derive soft thresholding from them. Right, just take a look at this and see how you might get soft thresholding out of it. Any questions about that? No? OK, we're going to see this operator, the soft thresholding operator, popping up a lot because it's what we call the proximal operator of the L1 norm. And we're going to see that it's extremely useful as are proximal operators in general in 2 lectures from now when we talk about proximal gradient descent. OK, without any other questions about the subgradients in general, I'm going to jump forward to the subgradient method lecture. So just to recap, 2 lectures ago, you learned gradient descent for a convex and smooth function that had no constraints and whose domain was all of Rn. That was the minimization problems we were looking at. Gradient descent basically just followed the direction of the negative gradient in an iterative fashion. So it updated xk to be xk minus 1 minus some constant tk times the gradient at xk minus 1. And it iterated this over and over again. And the step sizes we chose either to be fixed and small. And remember, we saw that if they are smaller than 1 over L, where L is the Lipschitz constant of the gradient, then we could prove it converges. Otherwise, we could use backtracking line search to set the step sizes, which was more adaptive and perhaps more effective in practice. And in either case, fixed and small or with backtracking, we proved that if the gradient was Lipschitz, then this algorithm has a convergence rate of 1 over epsilon, which means that if you want to achieve an epsilon suboptimal point, so some iterate xk that has a criterion within epsilon of the optimal criterion value, then you only need to go on the order of 1 over epsilon iterations or steps in this gradient descent algorithm in order to get such a criterion met. What are the downsides? The downside is that it required the function to be differentiable, and we're going to handle that this lecture. We're going to present a method that does not make this assumption. It can also be slow to converge. So that was another downside we said. We saw that actually the optimal rate of convergence was actually 1 over the square root of epsilon. We were told through some theory that we didn't prove that a lower bound for how well a first-order method could do was 1 over the square root of epsilon in terms of its convergence rate, which is faster than this. So we're left with the question, is there a method out there, it's a first-order method, that does better than gradient descent in terms of its convergence rate? And we're going to see the answer is yes. We'll talk about that next lecture. And in fact, we're going to see that much more than this is true. This same method actually applies both to smooth problems and a big class of non-smooth problems. So we have a really kind of powerful framework we're going to learn next time. Today we're going to talk about subgradient method, which is, in a sense, it's the most general optimization method you'll learn in this course. It applies to pretty much any problem that you'll write down, as long as you can derive subgradients. And that's really its strength, is its generality. All we're going to say is that f is a convex function. We're going to say its domain is all of Rn, although that is not really too important. And we're not going to assume it's differentiable. Okay, at this point, we're going to think about the problem of minimizing f without constraints. But if we're not assuming that the function is smooth, what happens if I had constraints? What could I do? This might not be the easiest way to approach the problem, but if I had constraints, we saw we can always rewrite a problem with constraints as f plus an indicator function. Right? We saw how to drive subgradients of that. So in principle, we could use this method with constraints as well. Okay, just create an auxiliary criterion that incorporates everything with an indicator function and try to apply a subgradient method to that. So in principle, that will work, although it's not necessarily the best way to do it. And we'll talk about constrained minimization next time as well. So the subgradient method is like gradient descent, although we just replace gradients with subgradients. Okay, so at every step, we just, instead of taking the gradient of the function, because it doesn't have necessarily a gradient, it's not necessarily smooth, we just take a subgradient at the point xk minus 1, and we update our current guess xk minus 1 in the same way. Just move in the direction of the negative subgradient now, and that becomes xk. Okay, so this gk minus 1 is just any subgradient of our function f at the point xk minus 1. So unlike gradient descent, the first thing that you'll notice if you implement this method on any example that you want is that it's not necessarily a descent method. Okay, so we're not going to be strictly descending on the criterion each time by following steps such as these. So we have to keep track of the best iterate among all those we've seen so far. It's very easy to do in practice, right? We just keep the best criterion value, store the best criterion value you've seen, and just keep that, the point that achieves that and that criterion value aside as you run the algorithm. And then if somebody told you to quit after 10,000 steps, you wouldn't necessarily take the 10,000th iterate as your answer, because it may not have achieved the lowest criterion value. You just look back and say, well, what was the one I'd stored that was the best so far? Okay, so it's a simple modification, but it's not a descent method. So what are we going to talk about today? We're going to talk about how to choose those step sizes, TK, for subgradient method. Convergence analysis, we're not going to do this one. It's actually going to be on your homework. So your homework is going to walk you through the proof of the subgradient method, convergence rate. We're going to go through an example of the subgradient method that's kind of neat, an intersection of sets problem. And I want to spend some time on stochastic subgradient method and stochastic gradient methods at the end, because they're extremely relevant for kind of these big optimization problems that we encounter today. And at the end of the course, maybe one of the last couple of lectures, we'll talk about stochastic methods in much more detail. This is just more of a preview. So how do you choose those step sizes? For subgradient method, unlike gradient descent, the big difference is that we don't have an adaptive method to compute them at each step. Okay, it's not like, there's not the analogy of backtracking line search with subgradient method. So all the options that we're going to lay out have the distinction that they're all pre-specified rules. So of course you could choose the step size to be small and fixed, like we did with gradient descent. TK just set it equal to some common value t for all iterations. The other one that we'll look at is a diminishing step size choice. So we're going to choose the step sizes to meet the following two conditions. The sum of the squares of the step sizes is finite, as if I sum them up from k going from 1 all the way through infinity. But the sum of the step sizes themselves is infinite. So you might remember that just by the sentence square summable but not summable. So once we square them, it's summable, which means we have a finite sum of squares, but they're not summable themselves. If I sum them up, they diverge. So this is the idea that the step sizes are going to go to 0, right? They have to go to 0 for this condition to be true, the first one, but they can't go to 0 too fast, because they're actually going to be diverging if we sum them up themselves. Okay, so it's just a rule for choosing step sizes. You can actually see when you prove the convergence of the subgradient method on the homework why these two conditions are needed. You'll use these two right at the last step of the proof to prove that with these two you get convergence to the optimal criterion value. There are other choices as well of like prefixed rules for the step sizes. These are the most common, so we're just going to stick with them. What's an example of a choice you might make that meets these two conditions? What's that? Right, 1 over k here, right? So just take tk to be 1 over k, right? Because then we would have the sum of 1 over k squared converging to a constant. Sum them up from 1 to infinity. I think it's like pi squared over 6 or something. I don't know. Not sure if that's correct, but that seems familiar. But the sum of 1 over k itself does not converge, right? That's for large k. It's going to look like log k, so it's going to diverge. OK, let's just jump right to the facts, the convergence facts. These are the things that you'll prove on your homework. If x is convex, its domain is all of Rn, and f itself is Lipschitz continuous with constant g. So we're not assuming that actually the gradient of the function is Lipschitz. We're assuming the function itself is Lipschitz, okay, with constant g, which means that, right, if I look at the absolute value of f of x minus f of y, that's bounded by g times the norm of x minus y for all x and y in the domain. Then with this condition, we have a couple of theorems. The first is that if I choose a fixed step size t, and I run the subgradient method, and I keep track of the best iterate after k steps, then as I let this subgradient method run longer and longer, and I look at the limiting criterion value that I achieve, then I'm going to be suboptimal by an amount g squared times t over 2. So it's telling you that fixed step sizes don't actually necessarily converge to the optimal criterion value. They give you something suboptimal, and this is the amount they're suboptimal, g squared times t over 2. Okay, so if t is smaller, it's better. Of course, you get a better bound on how close you are to f star, but the algorithm is also going to run slower. Okay, so with fixed step sizes, this is the result. It's in stark contrast to gradient descent, right? For diminishing step sizes, the subgradient method satisfies this, which means that it's right in the limit. It's going to give us the criterion value. If I look at the best criterion value I've achieved after k steps, and I let the algorithm run arbitrarily long, we're going to get arbitrarily close to f star. So this is saying. OK, so these are kind of two classic results on the subgradient method. Where do these come from? So these come from actually a basic bound, which holds for any problem in which the criterion is Lipschitz with constant g. If we just call r to be the distance, just abbreviate the distance between our initial starting point and x star as r, the L2 norm, then after k steps we have the following bound. How far you are from optimal, right, in terms of the best iterate you've seen so far, is bounded by r squared plus g squared times the sum of these step sizes squared from 1 through k, divided by 2 times the sum of the step sizes from 1 through k. This is the bound you're going to prove on the homework, with help, of course, to get here. But this is really, it just uses basic facts you know already about subgradients and convex functions. It's nothing super sophisticated in deriving this bound. So we can actually just read off the two results from that bound. And that's part of your homework, so I guess I won't go through it in great detail, but just let k go to infinity. You can see that if I had the diminishing step sizes rule, then the denominator is going to be infinite, right? And the numerator on the right is going to be finite. So this is going to converge. The right-hand side is going to converge to 0. So you're going to you approach the optimal criterion value. And this bound, this guy here, comes just straight from plugging in t. Ti equals t for every I. Okay, you'll see that as well. OK, another thing we get from this bound is actually the convergence rate of subgradient method. We haven't talked about its rate. We've just talked about the fact that it either converges with diminishing step sizes or it's suboptimal with some suboptimality bound with a constant step size. But we didn't talk about how fast it got there, right? Unlike gradient descent, we didn't really have a rate yet. You can actually get a rate from this bound. And now that I put this on the slide, I can't remember if Shashank put this on the homework as well. So if he did, there you go. This is the answer to one of the parts of the homework. I actually can't remember. But let's just go through it, because I think you can just see how you would use this bound. With a fixed step size, let's suppose I told you I wanted you to make the criterion difference between where you are after k steps and the best criterion value, or the optimal one, f star, that difference at most epsilon. Okay, then you might say, okay, let me try using a fixed step size. I'm going to make this bound at most epsilon after k steps, because that would ensure that the property you wanted was true. And to make that bound less than epsilon, I can actually write it as a sum of two terms when the step size is fixed, right? Because I just get r squared over 2 times k times t for this part, and this one is just d squared times t over 2. The t squared in the numerator and the t in the denominator cancel. So that's my bound. I can actually let's just try making each term at most epsilon over 2. Okay, see what that gets for us. So make that less than or equal to epsilon over 2, and that less than or equal to epsilon over 2. So that tells us what I have to do for t, right? So make this less than or equal to epsilon over 2. It tells me that t has to be equal to epsilon over g squared. I just get that from setting this equal to epsilon over 2. And in turn, that tells me what k has to be here. So plug in that value for t here, set this part equal to epsilon over 2, and tell you how many steps you needed to take. So it tells you both the step size, epsilon over g squared, and the number of steps. And the number of steps comes out just from plugging it in, ends up being r squared g squared over epsilon squared. Importantly, it's epsilon squared. Okay, so what has that told us? It told us actually the convergence rate, according to this analysis, is 1 over epsilon squared. So if I want a suboptimality of epsilon, I need to take on the order of 1 over epsilon squared steps. Compare that to 1 over epsilon rate that was achieved by gradient descent. It's a big difference, right? It's a lot slower. So think about if I told you that I wanted an accuracy, like I think we had this example last time. Suppose I told you that I wanted an accuracy epsilon of 1 over 100. Right? So with gradient descent, I need about 100 iterations to get that, say up to a constant. But with subgradient method, I need about 10,000 to get an accuracy of this kind. That's what 1 over epsilon squared is. So it's a very big difference, and you'll see that difference in practice. Yeah?
If f is Lipschitz, then it's differentiable almost everywhere. So with probability 1, every subgradient is also going to be the gradient.
So
well, not every, but every point that your algorithm traverses with probability 1, you're going to just be using gradient descent. So what's the...
let me try to rephrase the question. So it is true that if f is Lipschitz, it's differentiable almost everywhere. And the comment was that means that most of the time as I'm running gradient descent, I'll be at a point where it's differentiable. And so I'll just be applying gradient descent. So it's important to kind of try to make a distinction between what you think is happening probabilistically in terms of Lebesgue measure or something, right? Almost everywhere means that if I take the Lebesgue measure of the domain or something, then on a set of measures 0, it'll be non-differentiable. And what the algorithm actually encounters in practice. I can still have infinitely many non-differentiability points, right? And some of those may be basins of attraction for the algorithm. For example, let's think about minimizing the absolute value function, right? If I'm using the absolute value function as a penalty, then it's not differentiable at this point. But my algorithm, because this might be actually, the solution may actually be at a point where that component is 0, I may be encountering this point quite often in running the algorithm. Okay, so I may be visiting non-differentiability points quite often. It's nothing to do with probability. It's really to do with the behavior of the algorithm. I think it's good to challenge kind of the usefulness of these assumptions. I think that's very good. I just think it's important to remember, like I said, that it can have infinitely many non-differentiable points, and the algorithm may encounter those quite often. It's gonna hurt a lot. Yeah.
This is just I don't know how deep this question is, but is there a way to get the boundary K? Right now, this is the f of x of the best ones you see in K ranking, but is there a way to get it bounded in terms of K on the right-hand side?
It is there, right? It's just in the sum. So when t is a constant, this is what we get.
But in your previous slide, you suggested T not to be that.
Yeah. So okay, so maybe I can attempt to rephrase the question. This analysis may have been sloppy to get this 1 over epsilon squared rate, because we used a fixed step size. I actually bound each term by epsilon over 2. Are you asking if I'd used diminishing step sizes, would I got something better? Is that the question? Yeah, a different bound. So the answer is no. In fact, we're going to see later at the end of the lecture, this is a lower bound for non-smooth functions in general, for convex non-smooth functions.
So this was just a simplified analysis?
Yeah, it's an analysis. It gives us the right convergence rate. So maybe the high level is, I couldn't have done any better if I analyzed this bound differently. I would have also ended up at 1 over epsilon squared. We did make some simplifications to get there, but we didn't lose anything. You can maybe trust me on that for now. OK, so all very good questions. Do I have a slide? Yeah, I have an example now to show you really how different these two regimes are. The example is a penalized logistic regression problem where I'm given a bunch of points x, y, where x are some features and y is a label 0, 1. And I want to perform logistic regression, so I want to predict the label given features. And I'm going to do it with this logistic loss function. This is just the negative log likelihood of the logistic model, where I treat the logit of y given x as a linear function of x. So something you would have seen, say, in 701 or other classes. And the penalized logistic regression problem is doing this, so finding these coefficients beta with an additional penalty added to the criterion. And that penalty is either we're going to consider a ridge penalty, so this is the L2 norm of beta squared, or an L1 penalty or a lasso penalty. We're going to look at those two different cases. Okay, so just at a high level, this penalty is going to try to shrink the components of beta towards 0, and it's not going to set any of them really equal to 0. So it's just going to act a way of reducing the variance of our estimator, of our classifier at the end of the day. It's going to regularize it with a kind of a heavy hand, just make everything kind of smaller. This is going to selectively set some components of beta to 0, also acting as a source of regularization, so decreasing the variance in some way of our classifier. But in doing so, we're going to also, the nice side effect we see statistically from that is that it's going to tell us that some variables are more or less important, right? Because if the jth component of this is 0, then it means that the jth component of the features played no role in our classifier. So that was my minute summary of penalized logistic regression. Let's look at it from a convex optimization perspective. That's the criterion. This is its gradient. So this is something that I think is very similar to what you have on this last homework. On this homework 2, you guys are going to be minimizing a multiple logistic regression problem or a multinomial problem where there's just more than one class. So you'll go through a calculation like this very carefully. But this is its gradient. You can just maybe commit. You can trust me on that for now. It looks like yi minus the probability of being class 1 at the point beta. The point xi times xi. So this should look like the gradient for linear regression to you, right? In that case, this would just be xi transpose beta. So it's the mean in either case. That's how you can remember it. So that's its gradient. It's a convex function. That's its gradient. And we're going to try to minimize this problem, where p is either the L2 squared norm or the L1 norm. And in the former case, the whole thing's smooth, right? Because the squared L2 norm is smooth. so I can apply gradient descent to this problem. In the latter case, it's not smooth. Right? The L1 norm is not differentiable at 0. And so far, we've just done two methods, gradient descent and subgradient method. We really only have one option here, and that's to apply the subgradient method. So I've done that in this example. It's a very simple example, 1,000 points in 20 dimensions. So I'm trying to build a classifier in 20 dimensions from 1,000 training points. And like I said, for the ridge problem, I'm using gradient descent, okay, which is just going to move in the direction of this plus the gradient of this. Right? So it's going to add lambda times 2 beta to this. And the subgradient method is going to add this plus lambda times a subgradient of the L1 norm, and it's going to follow that instead. And the subgradient L1 norm, I think I've picked it in such a way that when the particular point is 0, like if beta j is 0, I've just chosen the subgradient to be something uniformly at random between -1 and 1. Okay, because any of them are valid subgradients. And you can see the difference in convergence. Right, so there's a huge difference in their convergence rate. So I've taken 200 iterations of each. This is plotted on they're both plotted on a log axis. Where we are after k iterations minus the optimal criterion value, this suboptimality gap. And you can see gradient descent really just converging very quickly compared to subgradient method with either fixed step sizes in black or diminishing step sizes in red. So I either chose it to be 0.001 or to be 0.001 over k, that's in red. And you can see that when I choose it to be 0.001, it doesn't have the property that it's a descent method. It's clearly not a descent method, right? It's going up and down all over the place. And it looks like it's almost asymptoted at about this level. So that's going to be about as good as we get. That's probably, it's hit the bound g squared times t over 2 for how suboptimal it is. If I look at diminishing step sizes, so 0.001 over k, then it's decreasing, but slowly. Okay, so nowhere close to as fast as gradient descent. Of course, this example is not perfect, right? These are different problems. The step sizes aren't exactly comparable. I tried to tune the step sizes in the two examples to make it as favorable as possible for each algorithm, just to make a point. I wouldn't take away from this the fact that this is the precise convergence behavior of subgradient method and the precise behavior of gradient method, and it's always going to be like that, or that this is a really perfect comparison. Just that roughly this is the kind of convergence behavior you should expect. Okay, so subgradient method is going to be a lot slower than the gradient method. Questions?
We always track the minimum during the fixed step size subgradient method, then it seems it will be better than the red line.
Yeah, good point. So the comment was if I just took the minimum, then I would be about here, right? But it still seems like you're playing a game of chance, right? Because the bulk of this convergence curve is not really moving. So you might just stay here. Yeah?
I didn't know when the point you found is the best point. Like, I thought that you're running the optimization algorithm because you're trying to find the optimal point.
Uh-huh.
I know what the optimal point is. How do you know?
You just evaluate its criterion, right?
Oh, I'm sorry. It's
So-
small. It's just
Yeah, just the smallest criterion of the ones you've seen so far. Yeah. Other questions? Yeah.
Does it mean if you take the diminishing steps, the subgradient method is always the same?
That's not true in general.
Okay, so just use
It looks true, yeah. I think it's my own practical experience is that it's often much more of a descent method with diminishing step sizes. It seems like it's much closer to 1. But I don't think that's true provably. I could be wrong. But it doesn't come out of the standard proof, at least that we do in the homework. Yeah.
When beta I equals 0, why not select the gradient 0 instead of select value from -1?
So I've done that as well. I mean, I've run versions of this picture with the different choices of what to choose for the subgradient. They look exactly the same. So if beta j is 0 and I just set gj to be 0, it doesn't change anything. Yeah.
You'll get sparsity by using subgradient.
That's a good question. So the question is, do you get any sort of sparsity? It depends where you initialize. So you're asking if I stop the algorithm after 1,000 iterations, whether I'll see points that are exactly 0 in the solution? It depends where I initialized. Let's write out the subgradient steps for this problem. Do we write them out? We should be able to just write them out. So beta plus, all right, so what I get at the next iteration, it's going to be equal to beta, where I was, minus t, some step size, times this. Right, where S is going to be either sine of beta I or anything between -1 and 1. Right, this is if beta I is equal to 0 and not equal to 0. So just staring at that.
The first line is coefficient.
Sorry? Yeah, I had that mixed up. Thanks. So just staring at that, you can kind of see the answer. It depends a lot where I start, right? So, and it depends how I choose the subgradients too. If I choose the subgradients to be 0 whenever the component is 0, then this is not going to contribute anything non-zero for non-zero components. Depending on where I start, if I start with, say, the entire 0 vector, then this is also going to have, this is not going to initially populate any components of the solution. So now it's about the gradient. I don't think you'll get exact zeros, actually, running the subgradient method, necessarily. Yeah, I don't think so. But so we will with proximal gradient. That's one of the examples, one of the advantages of proximal gradient. We'll learn next time. So you'll get things that are very close to 0, the solution. Okay, good questions. Let's take a quick break, and we'll come back and do an example and then stochastic stuff.